Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Very good morning. Now we will cover lecture 6, which is the stress transformation, and we will cover examples of applications because I think that we need more examples to better understand the Mohr circle. Okay, so there are cases where you have stresses like this of a point, and then you can add more stresses to that point. So we can superpose these stress states. So superposition of the stress state of any point can occur when the structure is subjected to the first load, which causes the first stress state. This is the first stress state because of the load applied, and then the structure is subjected to an additional second load, causing the second stress state independently. So we can combine these two stress states by rotating the stress element into a common plane or common orientation where the normal stresses are in the same axis. So in the first stress state, the normal stresses is not perfectly horizontal nor perfectly vertical as compared to the one in the second stress states. So what we do is that we can orientate the stress element to be in the same direction of the second element, and then we can combine them to determine the resultant stress. So how do we rotate this? Is by using the Mohr circle. I'll show you some examples later on. So here is an example where a stress state of A, this is the stress state of A of a point. It has a 10 megapascal compression on the X phase and positive 10 megapascal shear stress, and also 20 megapascal on the Y phase. I didn't put all the stresses of the shear stress. It should be there, okay, covering all. And then another stress state B is imposed on it. So B has a stress condition or stress states which is all normal stresses, which is, as we now know, it can be the principal stress, and this is oriented 30 degrees clockwise, counterclockwise 30 degrees from the horizontal line. Okay, so determine the new stress state. So when we superimpose this, okay, determine the new stress state and the principal stresses. Sketch the Mohr circle for the new stress state. So this is an example, and you can find this typically in a lot of examples or textbooks. Yeah. So you have a stress state A, yes, and then you add some more stress states, but in a different orientation. And what is the resultant stress for these two? So what we'll do is we are going to rotate. So what is the solution to this? So the solution to this is that we can rotate element B here to be in line with element A, okay? Because element B doesn't have a shear component, so it's easier for us to draw. And then, or in this bracket, you can also rotate element A to be in line with element B, okay? We'll do that later on, but in the first example here, we will do where we will rotate element B to be in line with element A. So what we are going to do is we are going to rotate this element to be in this form. Okay, so we do not know what is the value here. Might have some values, but let's draw this first. Okay, and this maybe we say sigma x b dash. B is the stress state, so this is sigma y b dash, and this is the tau x y b dash. And from there we can add to this. Now we can add to this element. So how do we do this? So what we need to do is we need to find, this is where the elements of B rotated, we are rotating it 30 degrees counter 30 degrees clockwise. So we rotate 30 degrees clockwise. Yeah. So what we are doing, we are going to rotate this 30 degrees clockwise. So what do we do? So basically in a Mohr circle, okay, in a Mohr circle, we have sigma and tau and 0. And let's say this is 20, 10. So 10, 20. So this is 20, 10. And you don't have anything else here. So this is your X phase. And this is your Y phase. And that is your small circle. So this is the center line. And we need to rotate this by 2 theta. 2 theta is 2 times 30 degrees. So that gives us 60 degrees. So we need to find the new X dash and Y dash here. Yeah. So we need to find the new X dash and Y dash here. So how do we find that? So we can do some basic calculation. We know what the OC is. Yeah. Sigma X plus sigma Y over 2. And that gives us like 10 plus 20 over 2. Yeah, so that gives us 15 megapascal. And we also know the radius because it's so simple. The radius is similar to the sigma X minus sigma Y over 2. Y over 2 squared plus tau xy squared. But here's 0. Yeah, so it's just the difference of this. So 20 minus 10 divided by 2 is 5. 5 megapascal. So we need to find the coordinate of X dash. So X dash would be our new coordinate. So so the sigma for X dash, for example. So we can find the sigma for X dash is OC plus R cos 60 degrees, cos 2 theta, yeah? So OC is 15 plus 5 cos 60 degrees. Cos 60 is half, so this is 17.5 megapascal. Similarly, we can find tau X dash equals to R sine theta. So R sine 60 degrees. So 0.866 times R. So we got 5 times sine 60. Hold on. So sine 60. 5 times 5 sine 65 sine 60. So it's 433. It's 433 megapascal. Okay, and so we can find sigma Y dash OC minus R is OC minus R cos 60. Yeah, so that is 15 minus 5 cos 60 degrees. That's 12.5 megapascal. And we have tau X dash equals to negative R sine 60 degrees. So it's minus 4.33 megapascal. So with that numbers, you should be able to draw the new Mohr circle. Yeah. So the new Mohr circle at that inclination, so we can now draw the Mohr circle at this inclination. So this Mohr circle now, this Mohr circle is the x surface is 17.55, 17.55. The tau is 4.33, tau is 4.33, and the y is 12.5 megapascal. Okay, and that is your new stress elements, which is now oriented to be in the horizontal direction, which is similar to this direction. Now you can sort of add them together. Okay, so this is the calculation that I did earlier for you to redo that if you want. Then you have elements set together, 4.33, 17.5, 17.5. These are in the same direction. We draw the stress elements which are now in the same direction, and then we can add them together. So 20 plus 12.5 is 32.5, and then 10 plus 4.33 is 14.33, and then negative 10, this is compression, plus 17.5 is the tension, it is 7.5 in tension. So this is the stress element, resultant stress element from the combination of these two stress states. So what do we do after that? After that, we will find we draw the Mohr circle of the resultant state. So we've got that before, so we can find the coordinates x and y. So the x surface or the x phase has a coordinate of 7.5, 14.33, and then the y surface has a coordinate of 32.5 normal stress and negative 14.33 as the shear stress. So we can now draw the Mohr circle of that. This is tau, this is sigma, and then we can say 5, 10, 15, 20, 25, 30, and so on. So 5, 10, 15, 20, negative 5, negative 10, negative 15, negative 20. Okay, so 5, 10, negative 20, negative 10, and this is negative 20. So we have got the first coordinate 7.5 and 14.33. So 7.5 and 14.33. And then we've got, this is our new x. And then the y surface is 32.5, and minus 14.33. So this is our y surface. And we are now ready to draw the Mohr circle of this element. Hopefully it will be just like that. So the lines, it's not a good Mohr circle, but anyway, let's clear that line. So we can connect these dots, for example, to draw our somewhat OC level, and from there we can draw our Mohr circle, which I think is a better one than before. Yeah, so this is our center. So from there we can easily find the OC. OC is sigma x plus sigma y over 2. Yeah, so it's 32 is 7.5, sorry, 7.5 plus 32.5 divided by 2. So it's 20 megapascal. And the radius is given by square root sigma x minus sigma y over 2 square plus tau square. Okay, and you will have square root of sigma r, 32.5, sigma x minus, so 7.5 minus 32.5 divided by 2 square. So it's 12.5 plus tau is 14.33. Okay, and you will have the radius. And you know your OC, and from there you can find your first principal stress, OC sigma 1, and sigma 2 is OC minus R. Okay, if you do that calculation, you will have the answer as prepared the answer earlier. So the radius is 19.01 megapascal. The radius is 20 megapascal, and your principal stress is given here. Sigma 1 equals to OC plus R, 20 plus 19.01 equals to 39.01 megapascal. And sigma 2 equals to OC minus R equals 20 minus 19.01 equals to 0.99 megapascal. So this is the answer when we rotate the element B to B with element A. Okay, so let's do the same thing now. Yeah, look at the same example. We will now rotate element A to be in the same direction with element B. Okay, so element B is rotated 30 degrees from the horizontal line, and we have to rotate element A by 30 degrees counterclockwise. So we need to rotate this. So if I can draw a line here with a red color or red color somewhere, so I need to now rotate this element to be in 30 degrees. Okay, so that I can add to this B element, so that I can add to this B element. Okay, 20, 20, and 10. So both of them are 30 degrees from the horizontal. So both of them are 30 degrees. So how do I do that? How can I rotate this? So I need to draw the Mohr circle for this. So if you look at here, I can find the x coordinate for this. The coordinate for the x phase is minus 10, is compression here, yeah? So like, look at this. This is 10 megapascal compression. This is positive 10 megapascal in the shear direction. So 10, 10. And then we've got the y surface is 20 tension and negative 10. Yeah? So if I draw the Mohr circle here, so I say 5, 10, 20, 5, 10, 20, 5, 10, 20, 5, 10, 20. So the x surface is negative 10. This is negative here, negative 10, and 10. So it's positive here. So x is here, and y is positive 20 and positive 10. Sorry. Yeah, y is 20 and negative 10. So negative 10, this is negative. So this is y. So you can now connect the lines. And we can draw a circle there. So we can now find what OC is. So OC is sigma x plus sigma y over 2. So we know what OC is. It's sigma x is sigma is minus 10. Minus 10 plus 20 divided by 2 is 5 megapascal. And then we have the radius. So the radius of the circle is given by r sigma x dot sigma y over 2 plus tau. So sigma x sigma y is 10 minus 10 minus 20 minus 10 minus negative 20 over 2 squared plus tau, and our tau is given by 10. Yeah. So we have square root of sigma x minus sigma y minus 10 plus 20. 10 is 20 minus 10. So you can find the r, and from there you can start to do the so I've got my answers here to be 11.18. So 11.18 megapascal. Now we know that our xy is in that direction, and we need to know what theta p is. Theta p is this angle. Yeah. So I need to know what theta p is. This theta p is the angle here from the horizontal line. So that theta p is given by, we can calculate by using tangent inverse. So we know the height here is given by the shear stress, which is like 10 megapascal. 10 y over x, this is 10, and the x here is given by the difference between so 20 minus is the halfway between, so it is it's also 15, I guess. It's 20, 10, 13, 15. Yeah, this is 15. 10 over 15. Yeah, so we can get that angle also. From there, we need to rotate this. We need to rotate this element by 30 degrees. Yeah. So from here, this is where our element is. We need to rotate another 2 theta, 60 degrees. So we have to move from here to here. So I'm going to draw this line in orange so that you have some ideas that I have to rotate another 60 degrees here. So I'm going to move here by 2 theta, 2 times 30 degrees, 60 degrees. So I have this angle here, theta p. So in overall, my total angle, so my total angle theta equals to 60 degrees plus theta p. So when I get here, I need to find the new x dash, y dash coordinates so that I can draw the stress element. So I've done that beforehand so that I have a consistent answer to you. So I've done that the r is equals to 18.03, 15 plus 10 square, made some mistake here, and the OC has, so I've done that, the OC has been calculated to be 5 megapascal, then R is 18.03 megapascal, and I have to rotate that by 2 theta. So I know this angle is the angle where my stress elements are. Okay, this is where my stress, although on the Mohr circle drawing is not horizontal, this is where the horizontal is. Okay, so if I can draw these elements here, it looks like this. If I can draw the element, so it now looks like this. So it is 10 compression and 10 shear stress and 20 in the y phase. So that's how it looks like along this line. Okay, so now I turn it by 2 theta. I'm turning it by 2 theta 60. So I've got this 60 degrees. I've calculated it to be 60 degrees. And I know that theta P is calculated to be 33.69 degrees. Okay, you have to do this calculation yourself. It's just tangent theta. This is 10. This is 15. Yeah, so y over 15. So this is 15, this is 10. Vertical is 10, the horizontal line is 15. So you get your tangent theta, the inverse of which is 33.69 degrees. So from this line to this line, this is 33.69 plus another 60. You have to rotate it by 93.69. So the total angle of theta that you need to rotate, so theta total you need to rotate is 33.69 degrees plus 2 times 30 degrees. So you will get 93.69 degrees. It means that you have to rotate 93.69 degrees here. Yeah. So that is the angle that you need to rotate this guy. So when you rotated that, you can now find the coordinates of these two things. You can now find the coordinates here, the new y surface. This is y, the original y, and then you rotate it by 60 degrees. And then this new x surface, initially x surface is here, you rotate it by 60 degrees. But it's difficult for you to find the calculation based on this line. So what you did is you've used the horizontal as the baseline, and then you get the theta total as 93.69 degrees. So if you do that, you will now have 33.69 plus 60, and this is the new location. So you can do your calculation of the new coordinates of the y dash. This is the y dash, and this is the coordinate of the new x dash. So the new y dash has got two components, the sigma and the tau. So y dash is OC plus r cos 93.69. So 5. So the r has been calculated 18.03. We will get 3.84 megapascal. And you know your shear stress Ty dash is r sine 93.69 degrees. It is equivalent to 18 megapascal. And look at x. You want to find the new coordinate for x dash. Is sigma x dash equals to 5 minus 18.03 cos 93.69 equals to 6.16 megapascal. And tau x dash equals to minus 18.0 megapascal. And you can now draw the new element. So tau x dash is the new shear stress at the x surface. So this is the x face. Negative means it will show downwards. And then sigma x dash is 6.16. Positive means it's tension. Similarly on the y face, do I need to draw this to tell you that this is the y, the x face? And do I need to tell you that this is the y face? So on the y face, we have got we have got the stress element. Sigma, the normal stress element is 3.84 in tension, positive, and tau I dash is negative 18 point. It's positive 18.0 megapascal, so it's rotating counterclockwise on the y dash. You have to follow the nomenclature as we have done in the previous lecture. So then, what do we do? When we have the stress element, we now can put it side by side with the stress element previously. So we put the element side by side. Initially, it was like this. Okay, so initially, I have to put this differently. This is the initial state. This was the question that was given to you. But what we did was we rotate this element. We rotate our element A to be in line with element B. So when we rotate element A to be in line with element B, this is what we get. 18, 6.16, and 3.84. Okay, so with that we add them together, and 10 plus 3.84, we got 13.84, and this 20 plus 6.16, we have 26.16, and then 18 is in this negative direction, so 18 megapascal. So we now have a stress element which is rotated 30 degrees from the horizon, and we combine them together and we've got this resultant stress. So this is the resultant stress. Let me box this in yellow. So I box this in yellow and say this is the resultant stress. Okay, so resultant stress, or the superimposed stress, or whatever. Okay, so once we get that, that's a normal procedure. After that is to find the draw the Mohr circle in order for us to find the resultant element. So here is the case where we have our element here, and on the x surface kita ada coordinate 26.16, and this is negative 18. So on the x face I've got 26.6 and negative 18, and on the y face I have 13.84, and it has to be positive 18. So what do I do after that? I'll draw the sigma tau coordinates, and my coordinates, this is about 26, this is 10, 20, so this is, let's say this is 10, 20, so this is like 10, 20, and then this is 26. So this is 26.16 and minus 18. That's my, and the y coordinate is 13.84 plus 18. Okay, so from there I can use this data, to calculate the value of my OC. So OC equals to mean value of sigma x plus sigma y. So sigma x plus sigma y over 2, 26.16 plus 13.84, which is 40, divided by 2. So I have 20. And r can be calculated. This is the radius of the circle. Is the difference between the mean of the difference. So 26 minus 13 divided by 2. You've got 6.16. And then the tau is 18. And we have calculated the radius to be 19.01. So that is our radius. That is our OC. So when we have our OC and radius, it will be just a straightforward thing to calculate the principal stress. And our principal stress is given by sigma 1 equals to OC plus R equals to 20 plus 19.01. 39.01 megapascal is the maximum stress that happens because of these two superposed elements. And then we have sigma 2, which is OC minus R, which is like 20 minus 19.01, and we've got 0.99 megapascal, which is the minimum stress that occurred for these resultant stress elements. So when we compare the results from these two approaches, we have got the same answer, where if either we rotate A to match B or we rotate B to match A, we've got the same principal stress. We may not have the same Mohr circle, because the Mohr circle only represent the stress state of any point at a certain rotating angle. So what we find is the common answer would be the sigma 1 and the sigma 2. The principal stress, i.e. the stress, maximum stress, and the minimum stress for the circles are still the same. So we compare that, and you then